Hello, and welcome to the Honeywell Pilot Familiarization video covering a deep dive into a few important FMS 6.1 features. I'm Rob Ehrlich with Honeywell's Flight Technical Services, and I will be discussing a few select FMS 6.1 features in detail. In this video, we will be discussing temperature compensation, vectors to final, multiple approaches to the same runway. We'll also review R&P requirements and chart naming conventions, and auto LNAV on go-around. In this section, I'll be discussing temperature compensation and how it is used in the Honeywell FMS version 6.1. On September the 17th, 2015, a mandatory compliance requirement began for the FAA NOTAM on cold temperature restricted airports. The FAA Notice to Airmen titled Cold Temperature Restricted Airports, last updated on August the 15th, 2019, makes cold temperature compensation mandatory at specific airports when operating below specified minimum temperatures. What this means for pilots is that snowflake symbol, shown in the notes section of approach charts, now indicates that temperature compensation is required for the approach when the outside air temperature at the specified airport is at or below the specified value. The NOTAM identifies U.S. airports where conducting approaches that rely on barometric or baro VNAV for guidance at extremely cold temperatures could result in altitude errors exceeding the required obstacle clearance, or ROC, built into the procedure design. As previously mentioned, the snowflake symbol on the notes section indicates a minimum temperature, below which published altitude constraints must be compensated for based on the baro VNAV effects on altitude indication. In October of 2016, along with updating the list of airports, the FAA also introduced a simplified procedure for aircraft with a temperature compensation or temp comp function. What had changed? Aircraft which have an automatic temp comp feature in the FMS may use a simplified procedure now called the all segments method. There is no need to reference the restricted airports list for affected approach segments. Just look for a snowflake icon or note and a cold weather compensation temperature limit on the approach chart. If reported temperature is below the critical temperature for cold weather correction, pilots will select temp comp on the FMS and may correct all altitudes from the initial approach fix altitude to the missed approach final holding altitude. As mentioned, if the reported temperature is below the critical temperature for cold temperature correction, pilots will select temp comp on the FMS and may correct all altitudes from the initial approach fix altitude to the missed approach final holding altitude. Currently, published altitudes from the initial approach fix to the missed approach final holding altitude at affected airports are to be cold temperature corrected. Pilots must advise ATC with the corrected altitude when applying altitude corrections on any approach segment, with the exception of the final segment. Let's review a few key terms. Barometric vertical navigation, or baro VNAV, is defined by the FAA as an RNAV system which uses barometric altitude information from the aircraft's altimeter to compute vertical guidance for the pilot. It is important to note that all Honeywell systems use baro VNAV. True altitude is the height above sea level. Pressure altitude is the altitude of the aircraft above the standard datum plane, which is also displayed with the altimeter set to 2992. Indicated altitude is the altitude reading on the aircraft altimeter, and density altitude is the pressure altitude corrected for non-standard temperature. So why is it so important to compensate for altitude when extreme temperatures exist at airports? Since approaches are charted based largely on obstruction clearance, pilots must always know where they are in relation to required altitude constraints along an approach. Aircraft operating closer to the ground can present a concern for obstacle clearance. A barometric altitude reading can be affected by extreme temperatures. Hotter, less dense air will result in the aircraft being higher than the barometric pressure altitude indicates, as depicted in the high outside air temperature illustration on the left. We can see the true altitude of the aircraft is showing the aircraft to be higher than the barometric pressure altitude would show if it was used to follow a glide path. Colder, higher density air will result in the aircraft being lower than the barometric pressure altitude indicates. The low outside air temperature illustration on the right shows that while the barometric pressure altitude the pilot may be using shows the aircraft on the published glide path, the aircraft's true altitude is actually below the glide path, putting the aircraft in a non-protected portion of the approach. Because of this effect on barometric pressure altitude indication, pilots need to compensate for the difference between the indicated and the true altitude in order to ensure they are on the published approach path. Colder temperature airports, for example, would otherwise present potential danger as the aircraft dips below the designed glide path of an approach, leaving the aircraft vulnerable to obstacle threats, while the pilot may believe the aircraft is operating at the correct altitude. What hasn't changed? For aircraft without an FMS temperature compensation function, the following still applies. As stated in the FAA notice to airmen on cold temperature restricted airports, pilots familiar with the NTEP procedure for making altitude corrections and choosing to use the all segments method are only required to use the published snowflake icon and associated temperatures on the chart for making corrections. A manual calculation using the AIM 723 ICAO cold temperature error table is needed to determine the required add-on. Note that there is no extrapolation above the 5,000 foot column required. Pilots should use the 5,000 foot height above airport in feet column for calculating corrections of greater than 5,000 feet above the reporting station. Note also that compliance with temperature limits on RNAV GPS approaches is still required. Without a TempComp FMS function, pilots must consult the ICAO cold temperature error table in order to determine corrections for each altitude where there is a constraint, as shown in this illustration. From the current temperature, the pilot will reference the published altitude and read the correction number at the temperature and altitude intersection of the table. Needless to say, this additional step can add a significant workload to a usually high workload segment of the flight, the approach. Let's review a summary of a few important things to know about cold temperature restricted airports. Only airports with a runway length of 2,500 feet or greater were evaluated. Do not correct altitudes published on standard instrument departures, obstacle departure procedures, and standard terminal arrivals. Compensation is only required for the approach segment when it is required. Pilots must be cleared by ATC to apply a cold temperature compensation to an ATC assigned altitude, or when flying on a radar vector in lieu of a published missed approach procedure. ATC is not responsible for making any altitude corrections and/or advising pilots that an altitude correction is required at a restricted airport. Pilots may use real-time mesoscale analysis, or RTMA, alternate report of surface temperature, for computing altitude corrections when airport temperatures are not available via normal reporting. RNAV approaches to LPV minimums use a geometric glide path from the GPS which is not affected by the extreme cold or hot temperatures. However, temperature compensation can be used in conjunction with LPV approaches to aid in ensuring that the barometric path to the final approach fix is closely aligned to the LPV path that the aircraft will capture 2 nautical miles prior to the final approach fix. It is also important to know that the decision altitude, or the DA, must be compensated. Calculations will need to be made for the final approach fix, the precision final approach fix, the minimum descent altitude or decision altitude, and the missed approach final holding altitude wherever cold temperature corrections are required. It is important to note this is also true for ILS approaches. While the glide slope may be fixed, the decision height must be adjusted manually since it is a manual input by the pilot. Honeywell's FMS 6.1 Baro VNAV temperature compensation provides an automated means to compensate for temperature variations, resulting in a vertical path that more accurately matches the intended path. Using the FMS 6.1 TempComp function allows pilots to stay in compliance with the FAA guidelines and requirements for compensating temperatures at cold temperature restricted airports. The FMS 6.1 temp comp function will compensate all constraint altitudes for the approach, as well as for the missed approach, as required by the FAA Notice to Airmen on cold temperature restricted airports. The following list of actions can act as a quick reference to setting up temperature compensation in the FMS. We will discuss these steps in the following slides. First, you will need to set up the desired temperature compensation configuration. Secondly, enter an approach procedure into the active flight plan. Then enter the landing surface temperature in the Land Go-Around Init page. Next, verify the compensated altitudes on the temp comp pages. Then you'll select Activate on the temp comp page. And since either the minimum descent altitude or the decision altitude will have to be entered manually, calculate either of those compensated altitudes. And finally, activate the compensated altitudes for either the minimum descent altitude or the decision altitude. To set up the desired temperature compensation configuration, you will need to access the Flight Config page in the FMS. This can be done by selecting the Nav button on the MCDU. Press Next from the Nav page to get to Nav page 2. From Nav page 2, find the line select key, or LSK, for maintenance. Then select Next for page 2 in the maintenance pages. From page 2, select Setup from the options. From the Setup page, you will see Config displayed across the top with an option for radio on the left and flight on the right. Select the option for Flight Config as shown in the image below, and you will be on the Flight Config page. From the Flight Config page, you can view the current temperature compensation settings as well as access the Temp Config page to select from one of 3 temperature compensation settings. Selecting the Temp Comp Config page allows the pilot to toggle between settings: Off to disable the function, Cold for cold temperature compensation only, Hot and Cold for compensating both hot and cold temperatures. The next step on the list is to enter an approach procedure. Assuming the approach procedure has been set up, we will proceed to the next step, setting the destination airport temperatures. Once you have set up the temperature compensation configuration, you will need to set the outside air temperature, or OAT, that is reported at your destination airport. This is done by selecting the Perf button and locating the option to select Landing. The landing page will come up titled Landing Go-Around Init. This is where to enter the destination airport temperature. It will now be possible to compensate all required altitude constraints for temperature. Fortunately, from the Land Go-Around Init page, there is a shortcut to Temp Comp where you can complete the setup. From the Temp Comp page, you can preview all the compensated altitudes, which are displayed in inverse video on the far right of the page. Upon review of all compensated altitudes, the pilot selects Activate as shown. Please note that Temp Comp must only be activated one time to be in effect. It is important to understand what temperature compensation in the FMS specifically does in order to understand what is required of the pilot to ensure safe temperature compensated approaches are conducted. Let's look at decision altitudes and minimum descent altitudes. As you may already know, these numbers are not part of an FMS approach database, and therefore are input by the pilot as the approach is being set up. Decision altitudes and minimum descent altitudes are set with a setting external to the FMS. That data is not in the FMS and needs to be manually set. Approach-related alerts that follow are derived from that pilot setting. Therefore, any compensation to the approach altitudes will involve the pilot calculating the adjusted decision altitude or minimum descent altitude and inputting that compensated number into the system as the new decision altitude or minimum descent altitude. Fortunately, the temp comp function provides a calculator for the pilot to compensate the MDA or the DA. Let's take a look at that next. The temp comp calculator can be found in the FMS on the last available temp comp page, page 5. Page 5 provides the functionality to compensate an individual altitude for temperature as shown in the MCDU example. Using the temp comp calculator function, the pilot inputs an altitude value and views the compensated altitude. This function provides the pilot with the information needed to manually input temp compensated values, such as the minimum descent altitude or the decision altitude of an approach. Finally, don't forget to set the altitude preselect to the final approach fix and to set the compensated decision altitude, derived descent altitude, or minimum descent altitude in the approach minima window. The temp comp function will be canceled if the pilot sets the temp comp to off in the FMS flight config page, or deletes a transition, or changes the destination airport. Here is a list of some very helpful websites, including the FAA NOTAM and the updated list of cold temperature restricted airports. Let's pause here for a few seconds before we move on to the next topic. This section will cover the Vectors to Final FMS 6.1 feature. Vectors to the final approach fix transition is designed to permit the FMS to process ATC-guided vectored approach transitions. When the Vectors to Final function is initiated, the flight director drops LNAV and reverts to the roll mode. At this point, the pilot should manually select the heading mode. When vectors for an approach transition are being conducted, Fly Vectors to Intercept is displayed as the From waypoint. Selecting a vectored approach transition results in the Fly Vectors to Intercept message being inserted as a segment into the flight plan immediately prior to the final approach fix. In order to utilize the Activate Vectors option, the aircraft position must be within the terminal area of the destination airport, or 30 nautical miles from the destination. And the final approach fix must have not yet been sequenced. The design of Vectors to Final is to define a course to the final approach fix. Therefore, if the aircraft is already past the final approach fix, this setup would not be possible. As mentioned, the Activate Vectors prompt will make the Fly Vectors to Intercept prompt the From waypoint and drop LNAV guidance. When the vectored approach is activated, the FMS creates an approach consisting of an intercept or extended centerline leading to the final approach fix, and removes all waypoints in the approach prior to the final approach fix. Only the approach legs prior to the final approach fix are removed. The departure, cruise, and arrival legs remain in the flight plan. In this section, we will discuss multiple approaches to the same runway and how they are depicted. This section will also include a review of RNAV and RNP requirements. Multiple approach suffixes are published for both ILS and RNAV type approaches. FMS 6.1 adds a new feature allowing a selection from multiple approach options to the same runway when alphabetical suffixes are used to identify those published approach procedures. Initially, when multiple approaches to the same runway end were added, there wasn't any way to indicate this in the FMS. Later, suffix letters were added to indicate multiple approaches to the same runway. The capability to read these has been added to FMS 6.1. Before we look at some examples, let's review RNAV and RNP requirements. Let's look at RNAV and RNP and its requirements. While RNAV allows navigation from point to point defined by latitude, longitude, and independent of any ground-based system, RNP describes RNAV operations with onboard performance monitoring and alerting. This means that the pilot can readily identify the ability to meet the navigation requirements for the terminal procedure or en route airspace. Note that most RNAV approach procedures require an RNP accuracy of at least 0.3. RNAV approaches above 0.3 minimal accuracy are not permitted. In addition to monitoring and alerting, an RNP approach requires the aircraft navigation system have scalability, which means the capability to automatically retrieve the correct RNP value for each leg from the aircraft navigation database. As previously discussed, the aircraft must have monitoring and alerting capability. This means the system must be able to conduct a RAIM assessment as well as assess and display the accuracy. This symbol is the FMS 6.1 graphical display depicting the current estimated position certainty, or EPU, and the total flight technical error, or FTE. Similar to naming conventions for the runways with multiple ILS approaches, multiple RNAV approaches to the same runway are annotated with an alphabetical suffix beginning at the end of the alphabet and working backwards for subsequent procedures. These multiple types are included in the navigation database as defined. The FMS provides these approaches for selection. RNAV approaches have different naming conventions around the world. ICAO chart naming conventions call for the RNAV GNSS nomenclature as depicted. These approach charts normally provide LPV, LNAV, VNAV, or only LNAV minimums. All require some level of RNP capabilities. The chart heading displayed on the upper right demonstrates an example of the use of an alphabetical suffix used to depict multiple RNAV approaches charted to the same runway. The example shown depicts the RNAV GNSS Zulu to runway 04 left. Below the heading depiction, we can see the minimums as LPV and LNAV VNAV. Different from ICAO, FAA chart naming conventions call for the RNAV GPS nomenclature as depicted. However, LPV, LNAV VNAV, or only LNAV minimums are depicted similarly. In this example, we can see the RNAV GPS Yankee to runway 04 left. As you can see from the chart minimums depicted below the approach heading image, the RNAV GPS to Albuquerque has only LNAV minimums. Additionally, FAA naming conventions include RNAV RNP nomenclature as depicted for approaches which require a higher level of accuracy and RNP scaling. These authorization required, or AR, approaches which require FAA authorization will also be depicted with the alphabetic suffix when there is more than one approach charted to the same runway. The chart depicted shows the RNAV RNP Yankee runway 27 left to Chicago O'Hare Airport. ICAO chart naming conventions call out the AR for authorization required in the heading title, but are similar to the FAA RNAV RNP, as they similarly require a higher level of accuracy and RNP scaling. These approaches, which require ICAO authorization, will also be depicted with the alphabetic suffix when there is more than one RNP approach to the same runway. The chart depicted shows the RNP Zulu runway 01 right to Arlanda Airport in Stockholm, Sweden. In this section, we'll review the functionality of LNAV at go-around. As pilots know, a missed approach is initiated using a takeoff go-around or toga button on the throttle or via the missed approach prompt on the MCDU. Either of these actions inserts the missed approach into the active flight plan. If the missed approach is initiated pressing the toga button, all LNAV coupling is lost and the flight director reverts to the roll and pitch modes. The roll mode will level the aircraft. The pitch mode will initiate a climb. If the missed approach is initiated via the missed approach prompt on the MCDU, line select key 4 left, as mentioned previously, either toga or selecting the missed approach in the MCDU will insert the missed approach into the active flight plan. For RNAV approaches, LNAV modes stay coupled and the crew must reselect vertical modes. For all other approaches, LNAV VNAV coupling is dropped and the flight director reverts to roll and pitch modes, and the crew must reselect lateral and vertical modes. This concludes Honeywell's deep dive familiarization of FMS 6.1 select features. Please consult the Honeywell Pilot Gateway for more information regarding these and any other FMS 6.1 features for more information.